Okay, so this is another 5-minute question. So find the reaction that supported it. This is exercise number 2. This is point A and B. You have the uniform distributed load of 50 Newton per meter across the 4-meter length. So draw the free body diagrams and find the answer. Okay, this is another 5-minute question. Go try it. Okay, so that was roughly the times that you should be using on. So free body diagram, just redraw the whole thing. For the distributed loading, if you have distributed loading, you have to draw the outline of the distributed load without the arrow, and then place the FR in the centroid of the area. I don't know if you have covered that in statics, but we'll go into more detail on how that is done later on as well. Then you have to put the FR at the X bar. So it's going to be 2 meters. That's for the uniform loading. Wasn't the X equals 0, AX equals 0. Usually that's parent 10%. So grade yourself. If you miss anything, just take half a point off for each one of those that you miss. So at least you know. If you're not confident, I can help you grade it. Again, this is to check whether or not you understand the concepts of having a fixed support. Some of you may have missed the moment at point A. That means you are missing the fixed support. And this is to test whether or not you understand how to draw the free body diagram for the distributed loading. So again, you need to have an outline, you have to have an FR, and if you don't have those, just take points off accordingly.
Professor, is the MA it has to be positive, right?
Oh yeah, MA positive. Thank you. So if this is positive, that means this will be a negative. Thank you. See, that's very easy to correct, like the error that I have, because your friend pointed out that one thing, and I can trace the error, and I can just make a quick fix right there as well. Usually I give points for those who actually correct me. So can I get your ID number, please?
Right now, 6638.
663.
822 6721.
Okay, thank you. I'll add those to the assignment points. Last semester I do this, and then the people who like correct me the most is the one who already got an A. So, like, you know. So there are other people who like, oh, I need point, extra point to help me get the better grades, but ended up that, you know, those who correct me are just the one that already got A for the class. Okay. Any question about this before we proceed with the next exercise? The next, okay, I can still do it in the same page. This is going to be exercise number 3. Let me just write this. So what we say is we have a virtual section. If it's a virtual section, it means that you have a fixed support. Whenever you have a virtual section, always imagine that it's a fixed support. Okay, so let's say that we are doing this again. Similar example. But this time, this is going to be pin support. This is going to be the cable. And with the cable, I will give the dimension 3, 4. And I will have this right here, 400 Newton. So this is hundreds, 200s, hundreds, millimeter, millimeter, millimeter. So this is point A, point B, but I'll call this A, this is B, C, and D. So my question is, this is the section, virtual section BB in orange color. My question is, determine the internal loads at virtual section BB. So this required, I would say this is like a 15-minute question, require more work. I'll do the whole process with you once, just to make sure that you refresh your memory doing this. And then I'll issue another questions that you have to do by yourself. So first thing first, normally in this kind of problems, you need to do the free body diagram of the objects first. So the free body diagram of the objects is going to include this. Again, this right here, just to make sure that is right, just going to say that part is 100. So this is going to be tension T at D. This is 400. So right here, 300 millimeter, 100 millimeter. So when you do that, this need to be addressed as 3, 4. X and Y. So this is going to be your free body diagrams of that picture. From here, we're going to say that summation of the moment around A in the z-axis equals 0. And from left to right, I will have minus 0.3 meter. Some of you were asking whether or not you can do Newton millimeter. The answer is yes. Through the whole process, like later on during the second half of the semester, I will be asking you to do Newton millimeter as well. But at this point, the number, if it's in Newton millimeter, is going to be quite huge, so I don't get benefit of using that. So I will do Newton meter first. So this is going to be 0.4 meter, and then it's going to be, you still remember unit vector, right? This is going to be 3/5 TD. And that's going to be equal to 0. So TD is going to be equal to what? 120. 120 divided by 0.4 divided by 0.6. This is 500 Newton. And then, of course, summation of the force in the x equal to 0, have AX and minus 4/5 TD equal to 0. So AX equal to 400 Newton. And then the last one, summation of the force in the y equal to 0. We have AY minus 400 Newton plus 3/5 3D equals 0. So AY equal to 100 Newton. So again, this grade yourself 30% if you did that, but if not, don't worry. 20, this is 20%. If you feel any of this is new to you, that means you need to refresh your memory on statics. But then the problem is not complete yet, because I was asking for the internal loads. So it means that this one, this one, this one, this one need to be removed. I need to continue doing this. So this part was the was needed to do the more detailed part, which is going to be like, the statics, the mechanics of material. So again, this is going to be my AY. This is my AX. Now, there are things that need to be added later on. If you look at your textbook, I noticed some of you already checked the textbook. The textbook already have indicated that we have the shear force, we have the normal force, and we have the bending moment. If you read the textbook and you see that, that's fine. If you follow that protocol, that's okay. But I will go over that a little bit later. Okay, I will do this based on statics. So this is going to be my B section. So I will call this internal loading. This is my Fx. This is my internal loading Fy. This is my internal loading Mz. This is going to be the unknowns according to the axis. Now the problem that you have earlier, you already have xy axis. That's okay. You can keep the same axis system as before. But you still need to draw this in this picture as well, because it's a different free body diagram. So in this case, we already know that AX was 400 and AY, this is equal to 100 from previous calculation. So in this case, we're going to go through the process and say summation of the force in the x equal to 0. You have AX plus Fx equal to 0, so Fx equal to a negative 400 Newton. Sum of the force in the y equal to 0, you have AY plus Fy equal to 0. So Fy itself equal to minus 100 Newton. And notice that after all of this is done, usually I will mark the point. So for example, this is B. I'll take a moment around the point at the cross, at the cross section of the virtual section. So this is moment around B in the z-axis equal to 0. So from left to right, I will only have minus 100 Newton multiplied it by, I forgot what it was, 0.1 meter, and plus the mz equal to 0. So mz equal to 10 Newton meter. So notice that the whole process takes this much. So if this is the case, this would be 15% right here. This would be another 15%. And I have 1, 2, 3, 4, 5, 6. That means I have to divide it the rest equally. That means this is 10%, 10%, 10%, 20%, 10%, and 10%. Is that right? Yeah, that's right. 70% total, plus the another 15 and 15. So it means that when you work the problems in mechanics of material, the problem gets longer. You seem to be repeating the process of doing the free body diagram, doing the governing equation for the equilibrium conditions. Repeat the whole process, a lot more detail. And that's why the problem like this, rather than taking half an hour before, it should take 5 minutes, and then this one another 5 minutes, because the content of the mechanics of materials still followed. It's going to take more than that. How are we doing so far? Okay. If this is done without any question, I will give you exercise number 3, which is something that you need to complete this yourself. Let's make this L shapes. It's not really to scale, but I think this is good enough. So my question is still the same. This is A, B, let's say this is my point C, this is my point D. So determine the internal force, internal loads. Now when I say cross section, I would say this X section, BB. Now this should be a 10 minutes maximum, because you need to do free body diagram twice with all those calculations twice. So train yourself to do this in 10 minutes.
ก็เลือก axis เลยตรงนั้นไม่ได้แต่ว่า object view เป็นเส้นได้วัตถุคือบริเวณการจะต้องมีแบบ boundary ว่าเป็นเส้นไม่ได้มันต้องเขียน dimension ตรงนี้อยู่นะครับเพราะผมมีตรงนี้มีอยู่แล้วจริงๆตรงนั้นก็มีก็ดีไม่มีก็ไม่รู้ว่าอะไรเพราะตรงนี้
ได้400
ดีวะ
ดีกว่า500ใช่
Okay, that's roughly 10 minutes, I think. So again, we do the free body diagrams. You need to redraw. I cheated a little bit by copying this. In your exam papers, you have to just redraw. So this is my dy, this is my ax, ay. Again, from here, I'll just put x, y-axis over here. Let's see if I can find anything from the force of the x. So ax plus 400 Newton equal to 0. So ax equal to minus 400. That's the first. I need to only find my ay. So just in this case, along the way, since the problem itself will become longer and longer, there are steps that you need to do and steps that you do not need to do. So the problem itself, when I award a point, maybe something like this, I'll show you. So I'll take moment around, let's say which point would be best. I will take moment around this point. I'll call this C. And around C and the Z-axis for 0. So it means that from here, left to right, ax doesn't count. I'll have minus 0.25 meter times ay. 500 doesn't count, dy doesn't count, plus 0.25 meter times 400 Newton equals 0. So ay itself is actually equal to 400. So it means that this, I get my ax, I get my ay, I do not need to find my dy to proceed. Meaning that when this is only things I needed, if you get something else like, summation of the force in the y equal to 0, have ay minus 500 plus dy equal to 0, and even though you get dy equal to 100 newtons, this one will not be awarded credits. So the credit will be awarded to just this point, this point, this point. Because I only need ax, ay to proceed. Okay? So in the end, this is going to be my other free body diagrams. Quite the same as before. I have my ax, ay, and this one, if you want, you can still put the 100s. Again, this is going to be my fx, fy, and m in the z, x, y axis. And from here, summation of the force in the y equal to 0, ay plus fy equal to 0, so fy equal to minus 400 Newton. So that's the first. Summation of the force in the x equal to 0, so ax plus fx equal to 0, fx equal to minus ax, which is also 400 Newton. And then the last summation of the moment, I usually call this point so that if you make any error in finding fx, fy, it's not going to be a running error if you pick the point like that. So over here, I would get minus 0.1 meter times my AY plus mz equals 0. So mz itself, my AY was 400, so this is 40 Newton meter. So from here, again, marking this point, this point, this point, and this point, the score allocations, 15%, 15%. So this is 10, 20 maybe, another 10, 10, and 10. So 30, 60. So since this is not needed, this is like no point. I'll be adding like point somewhere. I don't know where. So maybe over here, 30%. Seems like the most difficult. The rest is rather straightforward, rather easy. So I'll say 10% for each one of those. So grade yourself. We have how many exercises so far? 3 exercises. Those 3 exercises, along with the grading, should be submitted in the in-class exercise in my course view by midnight tonight. I didn't set the time, otherwise I would set it by the end of this class. Some of you didn't bring the iPad or the paper, so you have time to do it at home. Yes?
Do grading have to put that percentage into the work looking at it?
Yeah, just check the grading and see how much score out of 10 that you get. That's fine. I mean, approximation. You should be able to guess. You should be able to guess. Because I'm going to try to have free body diagram as 30%, and the rest I should try to weight it equally, depending on the difficulty level for each part. So usually I would try to do that. Okay, we're going to take another break. We're not ending this class yet. We're going to take another break, and this time's a little bit longer, 10 minutes. But after 10 minutes, when we come back, we're going to learn some new things. So it's no more exercise. This is just the exercise we need to complete. Take your breaks. When we come back, we will try to do the rest.
We need to give them the whole class or just
This is fine because if you're taking statics, I would prefer that you have FY grade already. But then in this class, in the end, I would get rid of that. It has to be coming down. So you're coming down the right way anyway.
แบ็คกราวด์มันสีดำแล้วจะถ่ายที่แบบไม่มีฝั่งสี่ก็ยาก
I do it counterclockwise. Yeah, then should be okay.
ให้ตายหาที่ธรรมศาสตร์ไม่มีตอนวันไหนตุลา6 ตุลาเหมือนจะยิง2 รอบสิถามเอาสิถามทีม
ไม่แต่ว่าอันเนี้ยมันเปอร์เซ็นต์ยังไม่ครบอ่ะขายตัวเซ็นอันนี้สับลงไปก่อนเพราะว่าอันนี้ไม่ใช่จบทะเลแล้วก็อันนี้ก็ว่ามันเป็นวัดของตัว ไม่รู้อ่ะบางอันที่มันแก้ก็ไม่ได้ติดแก้ไว้อะแต่เนี่ยตอนแรกเราไม่ได้เขียนพี่คนนึงเราเป็น
เรารู้ตามคนอื่นว่าในแม็กวายและไม่ต้องวัดตัวนี้มันจะเป็นแอนตี้ใช้เป็นเอ็กซ์ที่บีเอ็กซ์เป็นบีแซดไม่ใช่บีเป็นแซดมันจะโดนตั้งชื่อโมเมนเทียให้เป็นแรงเป็นขึ้นด้วย MC
ยังจบไม่ครบอันนี้ขีดเส้นเอ็นหรือมันบรรทัดไม่บรรทัดอ๋อตอนแรกนึกว่าขีดเส้นตรงเลยอะไรเป็นไงเอ้ยเธอจบก็ไม่เราได้กี่เมตรอะไรกี่เมตรแล้วกี่ตอนนั้นเนาะ100 มิลทำสมิธให้มันไอ้สูง
เขาบอกว่าไม่มีหรอกกินคือแค่โมเมนต์ต้องขึ้นชุดก็ขึ้นมาแต่ว่าเอากินให้หนึ่ง
เอาไม่มีขายอะไรนะ
เคยถ่ายไลฟ์โฟโต้ด้วยไม่มีที่อะไรดี
ตั้งข้าวไม่มีที่อะไรดี
ก็แต่ก็โอเคแต่ต้องเป็นอเมริกาโน่อเมริกาถ้าเป็นกาแฟดำคนละอย่างถ่ายกิฟต์
เดี๋ยวกูเซ็ตไหม
เอามึงอย่างนี้ไว้ตลอดเลยมึงไม่ได้
เมื่อกี้กูถ่ายกูถ่ายมาตั้งค่าเป็นไลฟ์โฟโต้ไงมันก็เลยจะกลายเป็นที่ประมาณนี้
แม่งดุ๊กดิ้งว่าดุ๊กดิ้ง
มันเป็นเซ็ตค่าไอโฟนถ้ามันตั้งค่าไว้ไม่เป็นอย่างนั้นเดี๋ยวกูแก้ละ
รวมเลยอาจารย์สอนเข้าใจคนที่2คนที่3
มีลิงก์เขาได้1 มิลลิ
มิลลิแล้วก็อาจารย์สอนแล้วก็ทรายถึงเข้าใจอยู่แล้วทรายโอเคอยู่
โอ้ยแต่ฝ่ายกูว่าเขาไม่รู้กูชอบจากคนละส
จ
ลั
ริ
บ
งๆอ่ะกูคิดว่ามึงจำโดเรมอนได้ปะ
คนนั้นอีกคนหนึ่งคนนั้นอีกคนหนึ่ง
กูว่าเขาเป็นอาจารย์ที่สอนดีกูแค่ไม่ชอบเขาที่สุดกูสอนไม่ทันแต่เขาเป็นอาจารย์ที่ไอเดียที่สุดเลยคือวิชาการไม่ได้เก่งมากแต่สอนจริง
กูไปอ่านเลยกูบอกเลยมึงไม่ชอบแน่ๆเพราะอย่างนั้นที่มึงเจออันนี้กูบอกไอ้เนี่ยคือดีว่าฉันนี้มันไม่เสร็จสวยเลย
กูยอมแพ้คนนี้
มันบอกเลยแต่กูไม่ได้ทำเดี๋ยวมึงทำให้ไม่ได้มีเปิดบทแรกมาเจอเลยแค่ย้ายขา
อันนี้ไม่เคยอ่ะ
เห็นไหมทำเรียนไม่ให้ทำเลยเนี่ยเห็นไหมทำฟิสิกส์มันยังให้ทำเลยโอ้
ไม่คืออาจารย์ฟิสิกส์ทำถ้ามึงทำใส่อาจารย์แมทอาจารย์แมทจะร้องไห้ใช่ไหม
แต่ดีที่เคยทำแบบนี้
ส่วนตัวกูมองว่าแต่ที่ไม่เคยนี่พี่ผู้สอน
แต่โอยเริ่มเป็นคนคิดนะเว้ยวิธีนี้ไม่เคย
ใช่แล้วเขาก็ใช้ดีที่ว่าปกติเนี่ย
เขาก็ตั้งชื่อ
ไอ้เชี่ยเป็นดีบินโพซิชั่นอีกไอ้ยิ่งจริง
แต่ต้นตำรับมันเป็นเศษส่วนจริงๆนะเว้ยมันคือค่าสโลปอะมันเลยต้องวายส่วนเดลต้าแต่มันแค่ทำเล็กมากๆไม่ใช่ต้นตำรับมันคือเศษส่วนไอ้นี่มันไม่ใช่ฟังก์ชันมันไม่ใช่ไอทูเรฟสกิปบริบายเอาฟันนี่บุรีไปเอาไม่เอาไม่เอาไม่เป็นไรที่โน้ตมีของให้เขียนด้วยที่แล้วก็ไม่เอาของมาไม่เอากูอยากเรียนได้ไม่มีของไม่ทันของมาแบบติดตัวที่อยู่ได้มันกูกาปีกกูรอดไม่ได้ช่วงมวลมันเยอะไปแล้วแบบมันดิสติบิวไม่ได้สบายไหมใกล้ชิดอาจารย์มากโชว์ฝั่งเดียวดิฟอมโบเกินไปพูดเห็นกระดาษไม่ดีโฟมกระดาษกระดาษแข็งที่ทำมาจากปูน
เดี๋ยวจะไม่มีเวลาอยู่บ้านให้เราไปเที่ยวให้เรามาบอกเรามาเที่ยว
ว่างคนว่างแต่ว่ามันต้องแบบฝึกวัดคุณภาพตัวเองก่อนว่างคนว่างเยอะเราดูว่าพอเรียนได้เราลองกินเราคิดก่อนว่าจะลงมือใส่เพราะเราเป็นของวิทย์
This is the connector. Why is it limited? So this one I can write that.
เขาจะถามจานเลย
Oh, I'm using my iPad to write it. Yeah. From magazine office, you can get it from there. Đây rồi. ไม่ต้องใช้สูตรอันนี้ง่ายไม่ต้องใช้สูตรแต่ถ้าเป็นชั้นยากๆก็ใช้สูตรเป็นอย่างเส้นปลายของมันส่วนใหญ่จะเอาเส้นตรงให้เส้นถึงแต่เส้นปลายก็ได้เส้นปลายใช้เวลามากกว่าว่าเส้นปลายไงว่าทำไมสวยจังมันมีให้เลือกว่าเป็นเส้นปลายใช่จริงว่ะ
กรีดเช่าจะดูจนไหมเนี่ยวัดเอชุกไว้ฟอกวัดกรีด
ยูจะเอาของเก่าที่ผมทำเป็นของเก่าไม่ได้ถ้าจดไม่ทันก็ยกมือเดี๋ยว So we're going to restart the class pretty soon, whenever you guys are ready. Okay, I don't do any more recording for the class, and the main purpose of that is to make sure that you guys don't try to watch the video, to be honest, because from my experience, the people who watch the video, they tend to skip the video, and they try to just fast forward, get the screen, do the screen capture, try to understand by themselves because they thought it was faster. The problem with that is that a lot of time during this class, I do teach important points, but then I erase those points that I think you guys should not see that in the final write-up because it's an error. But I write them, explain them why this is an error, and erase them. So those people who watch the video clip, sometimes they fast forwards, they didn't listen. My experience is that about 70 or 80% of the people who watch the clips didn't actually watch the clips. So, I try not to do that. There's a request. I still have the video recording of the previous classes 3 years ago, 2 years ago. I think it was 3 years ago. I'll upload that just in case you need it. But I discourage you from doing that. Okay. So we have the machine. Usually the machine itself that we use to do this part of the test is called universal testing machine. So what it does is that they have what we call a solid block. We call it the crosshead, and then it will be connected to the two pole. Usually the pole itself, it's either a screw or hydraulics. And then it will have the driven machines. So it would have either a motor or hydraulic. And then of course, with this, the crosshead itself would be able to move up and down with the speeds we call the crosshead speed. The machine itself, on the tops, they will have a grips. The bottom itself would have a grip as well. Usually those grips would be made with steel, but the bite itself would be made with the diamond coating, so that it would be biting into any material and hold on to it very tight. So the grip itself, on the tops, usually it will be connected to what we call a load cell. And this is to measure the force. And what happened here is that in the middle, you will be placing the specimen. Usually, to make it a standard test, you have to follow whatever standards that we have. Usually, the basic standard is ASTM E8. This is for tensile testing. And it means that the specimen itself would have a certain shapes. Usually it would be a dog bone shapes with exact dimension. This is for repeatability. When you do the test, you have this specimen, you do the test, and then what you do is you attach strain gauge. Or sometimes you attach what we call extensometer. You can Google all of this and see the actual picture. But when you attach them, either those will be used to measure, the extensometer would be measure the displacement. This would be measure the strains, but then the displacement would be translated to the strains. And then of course you will be using caliper. Caliper would be the device like this to measure, the diameter of this. Caliper would be measure the diameter of the specimens so that you can get the area. And of course, force and area, you will get what we call the stress. Now, with all of that, this is the overall schematics of what we have as a machines. At the Faculty of Engineering, we have maybe like 10 different tensile testing machine, starting from small scale from the Chemical Engineering Department, where they do test polymer. And in the metallurgical engineering department, they do test metal. In mechanical engineering department, we do test metal as well. In the civil engineering department, they do test concretes. So all of this follow the same protocol, and what they do is they will have this calculation. So if you have the force, for example, this force, and say this is the area, the force divided by the area, we call it a stress, sigma, or stress. So the units that we usually take is going to be Newton per area. And usually area is Newton, the area is millimeter squared, not meter squared, in terms of the machine that we use. So this by itself is equivalent to megapascal, where your PA equal to Newton meter per meter squared. But Newton per millimeter squared is the common units that we use in the industry. So of course, if we get the force from the load cell, this from caliper, you can do the conversion and get the stress calculation from the measurement of the machine. And usually, with the deformable body, along the way, the area changes. So we have A0, which is the initial area, and AI, which is the instantaneous area. We're using A0 when you do the calculation. And when you're using A0, we call it, so F over A0, we call it engineering stress. And if it's F over AI, we call it true stress. True stress is impossible to measure because the area changes all the time, so there's no point of trying to find that exact cross-sectional area when it happens. So what engineer does is that we choose the initial area for the calculation, and then we try to see whether or not in the end the actual area after the deformation has changed a lot, and then they do the correction of the error later on. Quite the same, the strains itself, if you have the force pulling onto this, the object itself will be elongated. We call that elongation displacement or elongation. This is a symbol called delta. This is like a little musical notes. People would have to understand that this is sigma and this is delta. You have to understand the difference between the two symbols. The delta itself, if you divided that by initial length, this is what we call engineering strain. We also have instantaneous length. This is what we call true strains. And we don't do the calculation for those neither. So what we do in real life, we do engineering strain, we do engineering stress, but we don't do the true strain or true stress. So the reason why we do this is because whenever you want to explore a new material to see if it fits for our design, we have to do this kind of test. In my lab as an undergraduate, I have 20 of this tensile testing machine in my lab. And I have to supervise like the test running almost 24 hours, and we do different kind of tests all the time. Tensile tests, creep tests, fatigue tests for all kind of new material that we develop. So in this case, what we do is we pull the specimen until it breaks. When we start pulling onto them, it will develop the character, and you can actually do the mapping of the displacement versus the force. And you can actually convert that displacement into strains. And the strain itself, this is epsilon, or the strains. And usually we say it's an engineering strains. And this is the stress in MPa. Usually we pull onto it and we start getting the result. All metallics, all metal parts would have initial slopes being a linear slopes. So these linear parts the slope itself would be considered elastic modulus of the letter E. So it means that the relationships along this line, what happened here is that if you start pulling onto the specimen, it will go up, up, up the curve like that. And when you remove the loading, it will go down the curve and it will go to that 0. So what happened here is that this is what we call elastic region. Just like a rubber band. You pull onto it, you release the rubber band, it shrinks back to the original. In terms of the metal, if you look at the microstructure, the metal itself has what we call a grain boundary. Those grains itself, when they are formed, they will have, the orientation of their molecules. They would have like BCC, FCC, those are the kind of things that if you take the class, you will learn that. But what you see in the metal structure, you will see it as a grain boundary. Now what happened here is that in the grain boundary itself, you start pulling onto it, the grain will elongate it, but then it's like a rubber. When you remove the force, it will shrink back. So the grain will become the same. So that's what happened here. But then after a while, it will start curving. When it starts curving, we have in the microstructure, we call it a dislocation. It means that the grain boundary, some of the grain break off. You have a slippage of the grain. So you have, if you take the class, it would be what we call a Berger vector. You will have a slip between one grain and the other, and it will be completely moved, in reference to one another. We call that dislocation. And that dislocation will create what we call a permanent deformation. So this is what we call a plastics region. With a permanent deformation means what? Means that when you remove the loads from the machines, the curve will go back down, but it will come back down in parallel to the original curve, to the original elastic line. This would be the same curve, same E. This is true for all metal. And then what happened here is that they are part of the deformation that's being recovered. So it means that this part, this is a strain that can be recovered. So we call that elastic strains. And this is the strains that cannot be recovered. This is permanent, or we call it the plastic strains. That means after a while, the deformation becomes permanent. So if you have, for example, a paper clips, you bend it a little, it comes back to the original shapes, but you bend it to a certain point, your paper clips will deform. That deformation is what we call a permanent deformation or plastic deformation of the metal itself. Now, in our class, Mechanics of Material, we're going to end our analysis over here. That means we will only cover elastic regions of the material itself. If you want to cover plastic region of the material, you have to go to grad school, and you will be taking the class called Mechanics of Material number 2, or sometimes they call it Mechanical Behavior. And that's going to be considered the stamping process. So for example, if you want to go to the factory that do metal stamping for the car parts, for the aluminum part that they do stamping for the stove, or for the table in front of you, they do a metal stamping. Part of it is well, but a lot of part, they are just metal stamping. They have to understand the plastic deformation in order to make sure that it does not fail. So in our class, we say that if it's only the elastic region, that means our relationships follow this curve is going to be a linear relationships. And this is what we call Hooke's law. This is a linear relationships, Hooke's law. And what happened here is that if you have the specimen you only consider this part, what we call a gauge area, when you do the test. And we measure stress and strain in that area. Okay. One of the things that you need to know is that what happened in terms of the objects, if you don't have a round object, if it's a square object like this, you start pulling onto the two sides, and we call this X. So for example, let's say this is X. Looking at the top view, you will see that the object itself will be elongated . So this is delta that has been elongated. But also you have a shrink. So this delta is actually going along the line that you have the force acting. So this is like the force. So the delta itself increase the length, but if you look at other dimension, they shrink as well, because we have what we call conservation of volume. It means that the object itself, if you have rubber eraser, for example, in front of you, you can try to pull onto it. You will see that part of it being expand, the other part being shrink. That's because of the conservation of volume. So in this case, you would notice that with the conservation of volume, it means that there must be a strain in other direction as well. The strain along the force, we call it longitudinal strains. Strains of the axis, we call it lateral strain. And usually, if we have the strain in the X, that strain in the X will result in the strain in the Y and strain in the Z as well. But it will be a negative result, and usually by experiment, the result would be, if you have a strain in the X, you would have about 0.3. I would say about 0.3, but if you look at the experimental data, it would be like 0.25 to about 0.33. strain into y. And that is going to be a negative values. And then 0.3 strain into z. So strain into x will result in that. So if you pull 1 unit, it's not going to go at 1 unit, but if you pull 1 unit, it will be shrinking about 0.3 units on the other direction. And that value, we call it Poisson ratio. It's actually being derived from the experiment. You actually pull onto it, see if it shrinks on the other directions, and we take a recording data, and we say, okay, this is the Poisson ratio. So each of the metal would have the Poisson ratio between 0.25 to about 0.33. The golden number that I usually use would be about 0.3. So it means that if you take a measurement, Poisson ratio would be a negative values of, in this case, would be lateral and longitudinal, like that. So that's the Poisson ratio. Now, with this, it means that with the knowledge, we're pulling in just one direction. We have stress in just one, so the strain. So for example, if you only have stress in the x, strain in the x would be just the stress in the x over elastic modulus. If it's a axially loaded member, you only have the stress in one direction. This is just going to be a one-dimensional or 1D Hooke's law. But in real life, you may have stress in multiple axes. You may have stress in the x, you may have stress in the y, you may have stress in the z. So that's why we actually have what we call a generalized Hooke's law in 3Ds. So 3Ds, Hooke's law, or generalized Hooke's law, it means that if you have the strain in the x, it would be 1 over elastic modulus, stress in the x, minus the Poisson ratio, stress in the y, stress in the z. And we do this in all axes. So this would be strain in the y, Poisson ratio, stress in the x, stress in the z. And strain in the z, 1 over elastic modulus, stress in the z, Poisson ratio, stress in the y, stress in the x. Again, this is the material that was supposed to be covered in engineering material, but the whole class for that, we are shrinking it down to just like an hour. And you need to know just one-dimensional. But you have to know that it's a three-dimensional properties, because later on towards the end of the semester, we will revisit the three-dimensional property of this, even though along the way we'll be just doing 1D or one-dimensional. So in order to do this, it means that we consider in this class the limit point or the failure to be yield stress. Or sometimes we just call sigma y. But again, along the way you will see sigma y being stress in the y-axis as well. So if you see sigma y, you have to ask question, is this sigma y or sigma yield stress? Or sigma yield? So this would be our limits for this class. If it's beyond this, we consider it's a failure. We consider that we cannot do any more analysis, we cannot do any more calculation because our knowledge is limited to just a straight line, to a linear relationships. Which means you have to understand the proper values for the yield stress. Aluminum. Usually the aluminum is around 300 to 400 MPa for the yield stress. You can verify that with the Google to check the mechanical properties of the aluminum. Now, aluminum itself has many grades. So when you look for aluminum, you will see the coating as well. The aluminum that I was using quite a lot, it was 6061. The high-grade aluminum would be 7075. We also have aluminum grading like 20-something as well. But different aluminum grades mean they have different metal composites that will add the strength to the aluminum itself. Quite the same as the steel. The steel itself, if you look at the steel, the yield strength usually around 500 to 700 MPa. And quite similar, you look at brass or copper, around 200 to 400 MPa. Brass is a little bit softer than the aluminum, but sometimes brass would have more of the nickel component into it and it will become stronger. You need to know those numbers because a lot of time when you do calculations and you see the number exceeding the value that was supposed to be for the metal that you refer to in the class, you have to realize that, hey, maybe our calculation is wrong because our calculation is based on linear elastic deformation. So if you see anything beyond 1 gigapascal, you should know for sure that this is not it. You cannot do this. You cannot use this dimension. You might have to increase the diameter in order to make sure that the stress is lower than the yield. Something like this. Okay. That is one general thing that you need to know. The other thing that you need to know is that the elastic modulus, if it's for steel, usually it's going to be from 200 to about, I usually use 210 GPa. Elastic modulus for the brass, usually around 100 to about 120 GPa. Elastic modulus for the aluminum, 60 to about 80 GPa. So the number that I usually use, this one would be 70 to 10 would be the one that I use, 100 would be the one that I use for the brass. Depending on the composites, because you have different kind of metal composition for each material when you fabricate them. So the elastic modulus may change a little bit, but not so much. But the yield strength will change quite a lot depending on the component that you add into the elements. Titanium, for example, nickel, for example, those will be added into the metal to increase the strength. It will be a lot stronger with those. It is best that you do a Google search yourself to find out the proper values for those mechanical properties of the metal. Because when you go to the workplace, usually they will test your knowledge, and the most basic knowledge that they test you for the technician's point of view is whether or not you understand whether or not the metal has what kind of mechanical properties. They don't really have analytical skill when you talk about technicians. A lot of them do have it, but most of them don't have it. But they are quite capable of knowing the mechanical property for each one of those because they have to check against the order forms. The order form would be saying, okay, get the metal that has this kind of strength, and then they do checks with the spec sheets. If it does, then it's okay. Usually, they will be pulling the metal until it breaks. It's a fun thing to watch. So check out the YouTube videos, tensile test by yourself. Of course, there are several of those. The company that I use quite a lot is called Instruments. So search for these company names. They have different kind of machines that would show you exactly how they work in the industry. They're still using that today. They still use that in the factory that I visit in Taiwan as well. So this is a summary of engineering material. We're not going to talk about heat treatment and other things, but along the way I will talk about heat treatment as well. How many of you have seen like metal work when they do the knife from the heat from the stove? What they do is the metal, when you put it in the oven or when you heat treat them, we call it an annealing process. And usually with the annealing process, you try to make a grain boundary circle. And what you do is, if you have a carbon elements and you freeze them very quickly, or you kind of push them in the water, we call it quenching. You will have a different kind of metal structure. Pearlite martensite, and usually when you have a martensite, the metal would be very strong, and that's why you get a pretty strong blades when you do metal works. That is actually from the same kind of material. So even if we have same kind of material, if we put it in a different heat treatment process, you still get a different mechanical properties. So don't trust that if you order this kind of metal, you will get the same 600 MPa. You have to look at the heat treatment process as well. But again, that's beyond the scope of this class. But it's a good things to know. I will try to add those along the way. Next week, we will revisit some of the fundamental for the actually loaded member. So if you want to continue working, some of you start studying in the textbook, you should finish chapter 1, 2, and 3. And next week, I will do chapter 4 in the text, if you have the text. You guys got access to the course syllabus, right?
Yes.
Chapter 1, 2, and 3 is a breeze. You can go through them very quickly. All right, if you have any questions, stick around. I will be here to answer the rest of your questions. If not, that's the end of today's class. If I go at the speed that is too fast for you, you can stop me at any time to ask a question. I'll be happy to slow down. All right, see you guys next week.
เอางั้นเกิดทีนี้แล้วจบความหมด
ของปีหนึ่งมาเรียนเข้าได้ยังเมคานิกแมทเทียลเรียกคริสตัลสตั๊กชื่อ
ใช่มันต้องเรียนนิดนึง
รู้สึกว่ามันข้ามมันข้ามมาคอร์ส
ใช่เราไม่ได้เรียน internal loading
ไม่เรื่องแมทเทียลอะปกติปีหนึ่งเรียนเพราะกลัวไปขโมยพักไทยมาเรียนแล้วเราไม่ได้เรียน